to discuss another thing why we did SOI is the so-called short channel effect. But let's understand what is the meaning of short channel effect. There are two types of short channel effect, which some of you already mentioned in the last class. You try to remind me, right? One is the so-called VTH roll-off. VTH roll-off means that when you make the transistor shorter and shorter, their VTH, the threshold voltage, will reduce. Like this. I will explain more later, okay, when you have a shorter transistor. So this is saying that VTH reduce when LG reduce, okay. Another is so-called drain-induced barrier lowering. This is saying that the VTH reduce when you increase the drain voltage. Now remember, we did not derive actually, but we just take it for granted. But if you look at the elementary derivation, the threshold voltage is derived by using 1D scenario. Or even we did not derive, we talk about the inversion, the accumulation, depletion, inversion. When we do that, we just say that I have oxide here, I have gates here, I have silicon substrate, and then you go from accumulation to depletion to inversion. That is the 1D scenario, one dimension, right? You assume you have an infinitely large transistor, and then we just derive the equation, we get something like this. I don't need you to memorize this equation, maybe write in cheat sheet will be good, right? But in reality, that's not the case. Look at this transistor. It's not one dimension. It is two dimension. When you solve the Poisson equation, when you have a VD that is 0, you have pretty large depletion region. Okay, so that's why when you reduce the channel length, this depletion region kind of helping you to sustain the depletion region here. Remember, we need to go to depletion region and then inversion. This drain is acting as another gate. You can say, none of your business, drain. You are supposed to conduct current, not to help me to turn on the transistor. But unfortunately, it is a high potential. You naturally will understand that if the gates can change the potential under it, isn't that the drain should be able to do so also? While whether it's effective or ineffective, it does have an effect, right? So that's why when you reduce the gate length, right? Here is the VTH roll off. You reduce the gate length. Let me write it down. This is like you just reduce the VG, right? Then you get the VTH roll off. Because the depletion regions of the drain won't change when you reduce the LG, but then you help you to form the depletion under the gate before the gate is doing anything, right? So someone helped the gates to form depletion, then isn't that it's easier for the gates to do the inversion. Another thing is that, okay, say you have the same gate length, but now if I increase the voltage, right? So this one is like this. Let's say I change it to 5 volts. Then my depletion region will be even larger. So for the same gate length, if I increase the drain voltage, it is helping me to create more depletion under the gate. So it is easier for the gates to do the inversion. So as a result, I have a lower threshold voltage at high drain bias. And that's why it's called DIPO, drain-induced barrier lowering. When you lower the barrier, remember it's the barrier for electron to go from the source to the drain. So you reduce the threshold voltage. Right? So when we talk about short channel effect, yes, it's related to the gate being smaller, and then you have some effect. Two of the effect is VTH roll off. You make it shorter, you definitely will have a lower threshold voltage. And at the same time, when you increase the drain bias, you will reduce the threshold voltage also, but it's more significant. Maybe this is something overlook, right? More significant for short channel, right? SCE, short channel effect. When it is very long, you don't feel this string-induced bearing much because they are far away. But when it's short, you change the gate bias, the change of depletion will be felt much more. Make sense? So two things. We can look at the figure, then we understand a little bit more. Here shows the threshold voltage as a function of the gate length. This is an old paper, right? But it's still true. 4 micrometer. When you reduce the gate length, they are basically constant, right? From 4 point something to 1 point something. A constant threshold voltage because they're pretty much 1D. But then when you keep reducing the L effective, the threshold voltage reduces. Now at the same time, we have two curves. One is the linear threshold voltage, right? What does it mean? Linear means it has a low string bias, means it is under linear mode, right? Remember that we talked about the linear operation, which has VDS minus, should I do this? Maybe just VGD, make it easy. VGD, which is larger than VTH. Maybe you forgot, but that is what we discussed earlier. You are able to form inversion at the drain side. But when you have a large VD, you actually have VDG less than VTH, which, remember, we talked about the pinch off, right? So when you have a large VD, you actually have more short VTH roll off. From this point to this point, it's the dipole, the drain-induced barrier lowering. If you go from top curve to lower curve, this is dipole, drain-induced barrier lowering. But if you go from left to right, then we call it VTH roll off. It really doesn't matter whether we call it correctly or whether we use the right name. But I hope you can understand there are two processes. One is purely due to the shorter LG. One is related to the VD. Okay. Similarly for PMOS. Okay. Yeah.
Dr. Wong?
Yeah.
There are 5 different definitions of VTH. Which one?
They should have the same effect. Let's look at the next curve, then you may understand what I mean. So, yeah, he talked about different definition with VTH. So let's come to here. So again, what type of curve is it? Is it IDVG or IDVD curve? Can anyone tell me? On the left?
IDVGS.
Thank you. IDVG, right? Because we're plotting the ID, the drain current, versus the gate voltage. And in that case, then for each curve, we should have a given drain voltage. Right? Now, I'm plotting this as what? Log scale. So again, we see this subthreshold region. Remember? That's the subthreshold region. Now, so what he's saying that is that a five definition of threshold voltage. Actually, I'm not aware of so many, but you can have many definitions. But there are a few of them. For example, some people would define it as constant leakage current. This is pretty common for sub micron device. For example, they may say 1e minus 7, whenever you reach 1e minus 7 is the threshold voltage. For example, if for this curve, the threshold voltage is here. For this curve, it is here. So this one has a larger threshold voltage than the other. You can also plot it in linear mode and do extrapolation to get the threshold voltage based on the equation we learned earlier. Some people will also do the maximum GM and then do extrapolation, right? So many different ways depends on your application. But the main point, yeah.
So this definition you just talked about, where I've heard of this definition, where you basically just pick a threshold on the y-axis and then
Yeah.
wherever it crosses. Is there? How do you come up with that number?
So
For
this
what number of
number,
the threshold?
it how do you
The
come up
sensors do that.
how do you
Yeah.
come up with the definition of the current for threshold voltage? Is that what you ask?
Yes. Yeah. Yeah.
Actually, I don't know. I mean, how should I say that? You see that they have pretty strict line, right? So really doesn't matter which one you pick as long as within this region. Because this is not the one that you use to do the leakage calculation, right? Leakage is depending on at zero bias. And all you want is just the relative, because if you shift by that much for 1e minus 6, you approximately also shift by that much for 1e minus 4. But I really don't know. I mean, in the past, usually we just pick 1 nanometer per mic. No. 1e minus 6. But that is for advanced device. These are old paper. So sorry, everyone. These are all old paper, right? But I don't know. Yeah, maybe I just say I don't know. But I feel that it doesn't matter. Makes sense? For constant current method.
Yeah, I've seen some global foundry publication where they use exactly that method, and they decided, like, can't remember the numbers. So there was one threshold for PMOS and one for NMOS. It was several hundred nanoamps, but I never understood where they came up with those numbers as to what that threshold on the y-axis is.
Yeah. I also don't know how they pick it. But again, I feel that it really doesn't matter in all the analysis, even you change it. But then you point out one thing very important. First, of course, you want to look at IDRS. I don't know if IRDS, international, IRDS or IDRS, the roadmap. International roadmap for device and system, right? In the past, it's called what do you call it? ITRS, right? International Technology Roadmap, right? These are the document, right? All the experts from the industry, they came up, they sit together and then say, for next technology node, what should be the leakage? What should be the threshold voltage? What should be the on current? So they define there, but I still don't think there is a physical reason which to pick. Yeah. So just let's say I don't know, right? But I don't think it will affect our discussion. But then when you compare paper from different company, if you care about VTH, then you look at carefully what VTH they are talking about, right? What is the definition? It's okay. Okay, good, right? So just remind everyone, right? So let's look at it. It's good to take a look carefully. This is L equal to 2. Again, old technology, but it's the same. This dash 9 at L equal to, what do you see? When it is at 50 millivolt means linear mode. This is linear. Versus saturation, right? Do you see that? Yeah, I have larger on current, smaller on current for linear, larger for saturation, but they basically overlap when you go to subthreshold slope, subthreshold region. So they basically have the same VTH. But I changed the VD, right? It means that I have very small dipole, drain-induced barrier lowering. Very small because it's long. That's consistent what I said earlier, right? Now, if you try to go to very short channel, like 0.2 micron, you have this 2.9. This is saturation, this is linear. Yes, at high VG, I got very large current for saturation and small current for linear. Remember, this is log scale. But at the same time, when you come to here, the subthreshold region, look at this. You have very different threshold voltage for the same device. That is a large dipole. Now, how do we define dipole? It's not just the difference of VTH. I can tell you dipole is expressed as delta VTH divided by delta VDS. Okay, so for example, I change my VDS by 1 volt, my VTH may be changed by 1 volt also. Then we will say that it is equals to 1 volt per volt. Although they should cancel, but this gives a lot of information. How much the VDS will change, the threshold voltage will change when I change 1 volt of VDS. So this direction is stable, right? Now at the same time, let's only look at the 50 millivolt. So I don't have drain effect. You can assume that. If you compare this 2 micron to, right, this is the curve for 2 micron, right? And this is the curve for 0.2 micron, right? Both are 50 millivolt. This is the VTH roll off. So I'm just repeating what I said earlier, but looking it at different angle. So again, in this class, right, too much information. I would appreciate you try to just go through the slide and try to understand everything. Then you will understand a lot already. We are just repeating what we have said earlier, including how to understand this curve. Okay, so that is the drain-induced barrier lowering and VTH roll-off. Now, so these are some simulation we did. Here you see that at 300 Kelvin, from VDO 0.1 to 1 volt to 5 volt, pretty long, 0.5 micron. We do see this dipole, right? This is dipole, right? Now, but for 4 Kelvin, dipole is small. Do you have any idea why?
Is this because of those scattering effects, temperature-dependent scattering effects? And in fact, it's preventing the depletion region from being wide enough under the gate?
That might have some tiny effect, but the main effect is not this. It's because, remember, at 4 Kelvin, we're talking about this subthreshold, the constant current method. So it's in the subthreshold slope. Remember that they have the so-called abnormal subthreshold slope. So it was supposed to be very steep, but they all screw up because of the abnormal subthreshold slope. And so they all limited by the abnormal subthreshold slope. Just imagine that this cannot, due to something bad, all this is maybe 60 millivolt per decade. There's something wrong, all have 300 millivolt per decade from the beginning. Then you don't see a strong dipole signal. So the point is this. It looks like dipole is better, but it's just because everything is worse from the beginning. Now, however, for circuit designer, there may be some advantage, because dipole is kind of difficult to predict because it depends on your voltage bias. But if I'm designing a 4 Kelvin circuit, I know it's bad, but then I know that it won't change too much for this dipole. Then it might be easier to design a circuit. Okay? So just want you to link what we have learned earlier. Okay? Any questions?
Yeah. So for the middle plot, the drain-induced barrier lowering improved the turnoff current, right?
You say again?
Room temperature. At room temperature, the debulk improves the turnoff current, right?
You mean improve the current?
No, for the room temperature one, 300 Kelvin.
Oh, but this is not what it increased the current, but we do not want to have a large current.
Oh, it increases the current. Okay.
Yeah, it increased the leakage current. It was 1 picoampere. Now it becomes 10 nanoampere. Now that's one thing. Yeah.
Thanks.
And that's one thing I forgot to mention. Besides changing the threshold voltage, you also see the subthreshold swing is getting worse due to short channel effect, right? So let me also mention this. Also worse subthreshold swing, right? Because the slope is not as steep as before. Right, so same for the subthreshold swing. We don't see much degradation because it was limited by the abnormal subthreshold swing already. So how can we improve this? Well, you need a better design transistor. So in NMOS, they increase the doping, and because increasing doping, they need to add the halo, which we did not discuss, right? If you refer to the advanced structure, which we don't have time, but if you're interested, we can discuss in the future, or you read it. But our goal here is this. The short channel effect is due to this ugly depletion layer. Can we stop it? If you add the oxide here, right, then you don't have this junction. Then you have much less depletion. And that's why we want to use SOI. SOI can reduce the short channel effect in this perspective, right? So we say that SOI can remove the parasitic